Hi, everybody. Welcome to NASA's Kennedy Space Center and the NASA Social for the launch of the twin radiation belt storm probes. I'm Jason Townsend from the NASA social media team. Today is part 2 of the NASA Social. Yesterday, we had a great tour of the facilities here at Kennedy. We also had an exciting video call with the International Space Station where 5 of the folks who are in this room today, along with 9 of the folks from across the Twittersphere, had the opportunity to ask their questions of the astronauts who are living off this planet. But before we start going into too much detail, for the benefit of the viewers who are at home on NASA TV, just what is a NASA Social? Well, a NASA Social really is all about taking the online world offline. We invite our followers, our fans, and the social media community to have members come out here to the NASA facilities. We hope that they take part in these special events where we give them access to facilities and meet our passionate employees that most folks don't get the chance to do. But we also hope that they take this opportunity to share all about NASA with all of their followers online using social media. And it doesn't stop here now in this room. We're continuing on with more social media events out there. Just recently announced is the next NASA Social at the Goldstone Deep Space Communications Complex in California's Mojave Desert on October 15th, 2012. You can find out more about this and the NASA Social program at www.nasa.gov/social. But back to today. We hope you're following along online by following at NASA and at RB Storm Probes on Twitter, and that you like NASA and the Radiation Belt Storm Probes pages on Facebook, and that you follow NASA on your circles in Google+. And if you want to follow or join the conversation online, you're welcome to do so anytime by using the #RBSP hashtag for the mission and #NASA Social for today's event. In today's televised event, we're bringing to you some of the behind-the-scenes information about the twin radiation belt storm probe satellites. We hope you learn more about the mission as it seeks to explore the Van Allen radiation belts around the Earth. RBSP is scheduled to launch tomorrow morning in the early hours of Friday at 4:07 a.m. Eastern Time aboard a ULA Atlas V rocket from right here in Florida. Today, you'll hear from a variety of different folks who each have a unique perspective on this mission, from the hands-on science work to the big picture view of America's space program and how this mission fits into it. These speakers are part of this event. It's the 41st NASA social media event of this sort. It's also the 7th NASA Social, which were formerly called NASA Tweet-Ups. We're building on the recent success from earlier this month with a first for NASA. It was the first ever NASA Social happening at 7 different facilities at once, occurring simultaneously, where we all came together for an incredible experience for the landing of the Mars Science Laboratory Curiosity rover on Mars. It's experiences like these that really help share NASA with new audiences in new ways, and it gets shared in very non-traditional ways that show off the science and engineering work that we do here at NASA. We strive every day to promote the diversity of amazing work done here and to share our missions, programs, and the talented employees in ways that connect with everybody. The NASA Socials are just one part of this strategy, and that strategy is always evolving. We're always looking for new opportunities to connect with new audiences and share information in new ways. We're always exploring where the public is and figuring out where social media is headed next. We are on the most popular platforms now, and when new ones emerge, we'll go there too. So thank you for joining us for this event today and this experience, no matter if it's offline here in person or watching online today at home. We're glad you could join us to hear more about this incredible mission. And without much further ado, here to talk with us about heliophysics, the study of the sun and how it interacts with the solar system, is Dr. Barbara Giles, the director of the Heliophysics Division of the Science Mission Directorate at NASA headquarters. Thank you for joining us.
So I'm very, very happy to be here today to tell you about the radiation belt storm probes, and my particular job is to tell you how it fits in the broader context of what NASA is trying to do in the area of heliophysics. Heliophysics is about solar and space physics. It's about how the sun affects our Earth's near space environment. And before we talk more about that, I just want to tell you a little bit about myself and my connection with this mission. I started at NASA 30 years ago as a freshman at the university. And when I went to Goddard Space Flight Center about 15 years later, I had the privilege of, with Dr. Bob Hoffman, starting the first studies for this mission. Later, when I went to NASA headquarters, I also had the honor of procuring the payload, the instruments that would be on board. And now that I've been named director, I have this honor of being with you today. One thing I can share with you is that every one of those instrument teams have done absolutely the best job that anyone could have expected of them. The instruments on board are the highest quality, the absolute best instruments that have ever been flown in this region. I can also take a few minutes to brag on the Applied Physics Lab and the job that they have done building the spacecraft and getting the spacecraft ready for launch. There were several times over the past few years where APL has made decisions that in hindsight I can now say absolutely made this mission successful. It is being launched on time, within its cost commitments, because of some of those decisions they made. This is, in terms of a taxpayer investment, one of the best investments I believe that we have made in the heliophysics area, and it will pay dividends for many years to come. So let's see, the next thing, I know this is something that we really want to talk about. This is absolutely the most exciting time for science at NASA, I believe. As you know, earlier this month, we landed the rover on Mars, and certainly the excitement of discoveries on other planets are something that just really speaks to our soul. NASA is also all about understanding our own planet. And the Radiation Belt Storm Probes is a mission that will do just that. In particular, the questions we're trying to answer are, why does the sun vary? How does the Earth respond? And what are the implications for life and society? And so that's what you're going to hear about today, is how the Radiation Belt Storm Probes fits into those big questions that we're trying to answer. When we're thinking about why does the sun vary, about 2 years ago we launched the first mission in our program that's called Living with a Star, because we do live in the atmosphere of a star, our sun. It's the most important star, in my opinion. The Solar Dynamics Observatory, that mission gives you all of those exciting images of the sun that you've been seeing in the news and in print. The Radiation Belt Storm Probes is going to join that mission and will truly be able to make that connection between what is happening on the sun and what is happening in Earth's near space environment. So that's what I want you to know about the Radiation Belt Storm Probes, and I would love to answer more questions if you have them about the heliophysics program, about the Living with a Star program, about Solar Dynamics Observatory, or any of the other missions that we manage for you, for your program in solar and space physics at NASA. Thank you.
Who's got a question? Well, don't be shy.
Yes, my first question among many would be, how does what you're doing now compare with the historical Van Allen explorations of the early space program?
Oh, this is a very exciting mission. We've actually had a few missions that have advanced the science of the radiation belts over time. And the big difference here is that we're actually going to have instrumentation that covers the full range of measurements that we need to unravel the mysteries. And I think that Dave Sybeck, you're going to cover about that instrument range, about the full range of fields, particles, waves. We've got the 2 spacecraft that allow us to separate processes that act on time scales or spatial scales. That's going to be the big difference in this case. It's an incredibly harsh environment. It has taken us this long to build this mission because of that harsh environment. We had to advance technologies to the point where we could safely fly these missions through the radiation belts, sustain the measurements through big storms. So I think that's one of the biggest differences from time. We've learned a lot. Now we're going to be able, I hope, to nail down the different theories at play.
Other questions? Well, don't be shy, guys. It's your opportunity.
Because you are going into such a hazardous environment, how predictable is the degradation of the systems on board? Mm-hmm. Is there really a way of knowing that?
Well, we can always wonder whether we have understood everything that's coming before us. One thing that we do know is that we have flown missions through these regions for many years. We have a lot of experience on what causes upsets to systems. We have a lot of experience about how this environment might degrade systems, and we have designed against those. So I think we have a lot of good information, a lot of good experience, and I have every confidence that this mission's going to survive that environment just fine. We have a good track record, actually. I'll just brag on our track record for a minute. Is that in heliophysics, many of the missions that we have flown, they have design lifetimes. They're 2 years or 4 years, whatever the design lifetime is. These missions have typically exceeded those lifetimes by several times, and I think this one will as well. We have fuel on board. We're ready.
Are there plans to put in some type of an early warning system for solar storms and their effect on the planet or electrical grid?
Mm-hmm. Actually, we have, as part of the heliophysics program, we are currently managing 17 missions in orbit now. Several of them do have real-time data capability. It brings us data now on what is happening on the sun, a beacon so that after a day or two we see more information, and then once the events get closer to the Earth, more information. All of that data is fed to the Space Weather Prediction Center that NOAA manages in Boulder, Colorado, and they do issue warnings on a regular basis. If you haven't signed up for their warnings, they're really fascinating to come through your email. I recommend you just sign up for all of the warnings. It's just fun to see them come through and think about what's happening in the space environment real time. Maybe that's only me that I enjoy seeing that, but okay, I love it. I love it.
This question kind of builds on the last. I was wondering if you could give some more everyday real-world examples of what RBSP is going to apply to folks in their lives as far as maybe radio frequencies and measuring things that would potentially interfere with the mobile devices that we're becoming so dependent upon.
Mm-hmm. We'll be glad to do that. Now, Dave, are you going to go into some of that in a little more detail? So I don't want to steal Dave's thunder, but one of the things that I think is really important that doesn't come, in all of our literature about RBSP, but one of the things is that the instrumentation is really going to be able to measure many of the current systems that happen in our near-Earth space environment. Understanding those current systems, and then later using other spacecraft as well, understanding how that connects to currents on the ground, the geomagnetic induced currents that you hear about that affect the power grid, we're going to be able to make those connections over time, and hopefully we will have some models available in the not too distant future. We're working on that to really predict how that might affect the power grid. So that's my, I guess that's one of my dreams to come to fruition over the next 2 years. Now, Dave, I've seen your slides. You've got other good examples as well, so I won't steal those from you. Okay. He'll give
Okay,
those.
we got one more time. One
Yeah.
more question. Time for one more. Anybody? Anybody?
As the information comes back from the storm probes, will there be access to the data available online for the general public to catch up on any of what what it's picking up?
Oh, absolutely. One thing that NASA has as a principle is an open data policy. And so as soon as the data has gone through its initial processing, it will be available in a very short period of time. It's openly accessible. There will be plots and graphs and the raw data that anyone would be able to pick up and use in whatever way they'd like to. So we're gonna try to also put some interpretations out there as well as time goes on. When there's a storm, there'll also be some releases that help explain the data for the larger events. So we hope that you'll follow us in the future. Okay.
Okay. Thank you very much, Barbara. Thank you.
You're welcome.
So next up, we have Dr. David Sybeck. He's the RBSP mission scientist from the NASA Goddard Space Flight Center. So joining us here today, Dr. Sybeck.
Thank you. Delighted to be here. Delighted to be with your viewers on NASA television. I'm David Sybeck. I work at NASA's Goddard Space Flight Center. I'm the mission scientist for the RBSP mission. That means I work closely with NASA headquarters and the scientists and engineers at JHAPL to get the best possible science out of this mission and to communicate it to you, the public. That's my job, so I'm very happy to be with you here today. Okay, let's see. Should have a slide to go with my presentation. That's good. Okay, we've done that one. Check. Move on. Okay, so where do we fit in the big picture? Well, we're talking about space weather. We're talking about things that happen at the sun and connect to us here at Earth. The driver for everything we do and we study is the sun, the turbulent processes that occur on the sun, flares, explosions on the sun, blasts of plasma that come out from the sun, carrying the magnetic field of the sun outward towards the Earth, through interplanetary space, past the other planets to Earth. When those explosions and those blasts of plasma reach Earth, that's when interesting things start to happen. The Earth's magnetic field is our shield against them, but it's an imperfect shield. Variations in the solar wind, the sun, that are coming out shake and make the magnetospheric magnetic field, our shield, shudder and shake. They interject energy, particles, plasma into the Earth's magnetic field. They're the driver of geomagnetic storms, which cause disturbances in the area around Earth. They're the driver of auroral phenomena, the aurora that you can see at high latitudes in the sky at night. So where do we fit in the picture? We, with RBSP, are measuring that response at Earth, the response to these geomagnetic storms that are driven by things happening on the sun. We're a partner in a sequence of events. We're a partner with the other spacecraft that Dr. Giles just mentioned. We're looking forward to working with them. Let's go on to the next slide. We're interested in solving problems of practical importance. That's the Living with a Star program. It works on things like that. These are some examples of space weather effects. Space weather, things that can harm our technology or our astronauts in space. Perhaps they range over a much broader range of topics than you had imagined. Airline exposure to radiation in passenger jets passing over the polar caps, harm to spacecraft and satellites, harm to astronauts. Difficulties with communication in the polar region, difficulties talking to airplanes, difficulty with your GPS. These are all space weather effects. We're going to be looking at one particular aspect, the harm that radiation in space, in the Van Allen belts, can cause to spacecraft circling the Earth. We want to be able to predict what goes on. To predict, we have to first observe and understand, compare with other cases, other days, other spacecraft. Let's go on. NASA's Living with a Star program. As Dr. Giles pointed out, it addresses fundamental questions, very basic questions. How and why does the sun vary? What causes explosions? What about the solar cycle? How do we know that this is going to be a big solar cycle? As you all know, we're headed into the peak of the solar cycle right now. It'd be good if we could predict just how strong that solar cycle will be, how big its effects will be. How do the Earth and other planetary systems respond? We want to know because we want to protect our spacecraft, our assets, and predict what's going to happen on the ground. For example, power line transmissions at high latitudes, as Dr. Giles mentioned. What are the impacts on human and robotic explorers? These things can destroy spacecraft. So, what are we going to have to do? We're going to have to understand the basic physics. There's no first principle, no model for predicting what happens unless you understand the science that should go into the model. Just like weather forecasts, you got to go out and observe, you got to think about it, you got to put things together, and then you develop these complicated models for weather. We have space weather. We'd like to know how to mitigate or accommodate space weather. You can't call your satellites back in if there's trouble, but perhaps you can power them down or protect them. You can ask astronauts not to be out on spacewalks if something bad is going to happen. And we'd like to understand how space weather affects instruments, spacecraft, electrical circuits, surfaces in space, solar cells in space. These can all be harmed by space weather. If you know what's out there, you know how to design them and build them in future. Let's go on. The Earth's radiation belts are invisible to you and me. This is an artist conception. It's a movie. Go ahead and start the movie. They are out there pulsating in space. They can grow, they can wax, they can wane, stronger one day, weaker the other, varying on time scales ranging from minutes to hours through days to months, even up to years, all different timescales, all different kinds of variations. Some of them are global, the whole thing expanding in and out. Some of them are very local, ripples on a donut-shaped object circling the Earth, bouncing back and forth, causing things to happen. They're connected to the Earth, as Dr. Giles said. The currents and variations that happen in the radiation belts can have effects down on the surface of the Earth, primarily at high latitudes. That's where field lines lead on a bar magnet to the northern and southern poles. That's where currents would flow. That's where trouble could happen to power line transmissions or communications. Let's go on. So, what about RBSP? Well, this is what NASA hopes to get out of the mission, and this is what we're going to see. We're going to try to understand the hazardous environment that we face out there. We'd like to know what produces the radiation in the Van Allen radiation belts. What processes remove the particles from the Van Allen radiation belts, because they grow and wax and wane. What processes modify the radiation belts? That's what this mission is intended to address. I've got a statement there about the instruments on this spacecraft, but I believe, Nikki, you'll talk more about the instruments. Is that right? Dave, that's great. Okay. So, as Barbara said, we've got the complete set of instruments we need from the lowest possible particle energies to the highest, from tens of eV to more than a giga-electron volt. That's from very cold to very energetic. We've got composition. We know about protons, electrons, helium, oxygen. We're going to measure all the waves out there, the waves at high frequency, the waves at low frequency, the DC electric field, the DC magnetic field, the AC electric and magnetic field. Comprehensive instrumentation, a pair of spacecraft to determine cause and effect, a pair of spacecraft to determine the extent of various phenomena out there, a pair of spacecraft to tell us what's going on. Next slide. I think at that point I stop and take your questions and pass on the baton. I could be Nikki Fox, but that would be peculiar.
Questions?
So how much heliophysics luck was involved in sending the Apollo spacecraft through the Van Allen belts back in the 60s?
Okay, so actually the Van Allen radiation belts, the astronauts that were going out passed through them rather quickly, and they didn't do space maneuvers while they were in the Van Allen radiation belts. And as long as you would stay inside the spacecraft, you would be okay. So in that sense, there wasn't any, and the effects of the Van Allen radiation belts were known about then, so it was known not to do anything then. Once you're in interplanetary space, you might have problems with energetic particles coming from the sun, and there you would certainly not want them to be outside during a big solar flare and energetic particle event. The other astronauts we have to worry about are the ones in the space station in the Earth's magnetosphere right now. At the highest latitudes, it gets up to the footprint of these field lines, gets up to open lines open to the sun, and so there is a need to take care not to do extra vehicular activity during big events. Somebody else.
In light of the Higgs boson publicity at the Super Collider, are you prepared to theoretically detect something extraordinary that you're not expected to find? Be hopeful, in other words. Get your Nobel
I'm going
Prize.
to tell the honest truth right here. The most exciting things that come out of these missions are the ones you didn't expect to see. And so you have to keep your eyes open. All my career, yes, there's a certain set of things we're guaranteed to do. We're going to the right place at the right time, the peak of the solar cycle, the heart of the radiation belts. But it's the things you don't expect to see that are most interesting. If we get the biggest solar flare ever, then we're going to learn something really new and interesting. Or perhaps there's some phenomena out there that we just haven't considered. And yeah, that's what we keep our eyes open for. And that's the delight of the mission.
Is there any evidence that activity on the surface of the Earth affects the belt in any way?
Yes, there is. As a matter of fact, there is evidence that phenomena on the surface of the Earth can affect the belts. An example of that is lightning strikes. Lightning strikes in one hemisphere launch waves that travel along magnetic field lines up to the other pole, the other hemisphere. And the sort of waves that they launch are just the right kind to interact with electrons in the radiation belts, either energizing them or scattering them. There are plenty of people who believe that processes in the Earth's ionosphere, sudden disturbances, can launch waves up into the atmosphere, up into the magnetosphere and affect the particles. Yes, we're looking for that. And we want to work closely with ground-based people to check them out. Yeah.
I know it was stated yesterday that these two different spacecrafts were basically built for the cost of one. What is some of the advantages of having the two different spacecrafts in the two orbits as opposed to just one satellite?
If you were going to ask about the spacecraft design, I'd defer to Dave. But if you're going to ask about why have two, there's some simple reasons we've thought about at the start of the mission. The answer is two spacecraft tell you if something is happening first here and then propagates there. Two spacecraft tells you if it's widespread or very local, and the spacing is going to vary, as Nikki is going to tell you in a few minutes. Two spacecraft gives you a wealth of information that separates spatial and temporal effects, lets you know more. We've had one spacecraft missions before. We've never had fully equipped two spacecraft mission to tell us more details on what's going on. Crucial, crucial.
Is there any working theory as to why there is a clear area between the inner belt and the outer belt? Is there some mechanism that sweeps out those particles?
Yes, there are plasma waves in that region of space that can remove the particles faster than they can be put into that region of space. But sometimes that space is full of particles. And so during big storms, they get in, go across it, and get into the inner belt and can hang around there for a long period of time. And as normal, there are more theories than scientists, so we'll be checking out which of those theories work best.
Questions? Other questions? All right. Well, then, hearing none, we will go ahead and move on to our next speaker. We have, oops. Next up, we have Nikki Fox. She is joining us from the RBSP. She's the Deputy Project Scientist. So, welcome, Nikki Fox. She's at the Applied Physics Laboratory at Johns Hopkins. So.
Hi, it is my great pleasure to be here representing the science team today. I've been having an amazing couple of days. I've been at, I think, my 4th trip out to see the rocket today, which was awesome. And you've all seen it, haven't you? Isn't it nice? Isn't the logo fabulous? Yeah. Do you know that logo is hand painted? Okay, because so if you have a smooth fairing, then they can put like a peel on. You know, you just produce like a sticker and then you peel it off and put it on a smooth fairing. If you looked closely at ours, it's ridged because it's a 4-meter fairing, so it had to be hand painted. So there's an artist who specializes in this, and he got a projector, projected the logo onto the spacecraft, and it's actually, if you can, not the spacecraft, sorry, they'd be really mad if he painted the spacecraft, that's right, the fairing, and he got it really close, and he actually painted it in 3D, so the whole thing wraps around the vanes. It is amazing if you can, it's just, yeah, I'm sorry, thank you, I'm very excited. If you can't tell, I am very excited, okay? I've been saying for about 2 months now it's impossible for me to be any more excited than I am today, and in fact I'm still proving that wrong. And Liz, I did wear my radiation belt this morning. So I meant to put it on before I came in. Liz made me a radiation belt, and I'm sorry, I will nip out to the car and get it so you can all see her creation. So anyway, enough of me blabbing on. So onto my slides. So Dave did a really nice job, and I'm sure Barbara did also, of setting up why it's so important for us to understand the sun and the solar system connections. It's not just the sun and the effect on our planet, but all of the planets live in the atmosphere of the sun. So there are many things that we can study here at Earth that are directly applicable to other planets. For example, all of the strongly magnetized planets, so Jupiter, Saturn, Uranus, and Neptune, they all have radiation belts very, very similar to ours. Not necessarily the 2 structure that Dave was talking about, but there are very large radiation belts around these planets. Because they have strong magnetic fields, they actually kind of constrain and trap the particles into that region. So Curiosity is finding wonderful things on Mars, but it is not going to find a radiation belt there. So we are looking at things that are applicable not just here, but throughout the universe. The same processes that accelerate particles in the radiation belts actually cause the Crab Nebula 6,000 light years away to glow in X-rays. So it is fundamental physics that we are studying. Have the next slide, please, Mike. Okay, and this is a still, or is it a movie? Is it? I think it may be just a still. No, it's going to be a movie. Excellent. So here we see a big solar event coming in and smacking into the magnetosphere. This is a nice model from the University of Maryland, and showing how the magnetosphere responds to what's coming from the sun. So the easy thing to do is to look up, see the aurora, and say you've got a space weather event. Obviously, for radiation, you can't see radiation, so we have to send probes out into that region of space. Thank you. I feel like Vanna White. And now the next slide. Okay, so here we have a picture of James Van Allen working. This is when they were discovering the radiation belts. Basically, if there was a thought bubble above there, it would say, oh dear, what's this signal I keep seeing, and why is it cropping up? It wasn't supposed to be there. And after a while of trying to make it go away, they finally said, okay, we must have a radiation belt there. So it was the first discovery of the space age back in 1958, and that was what led to also fuel subsequent missions to go and find the outer radiation belt, because with Explorer 1, Van Allen found the inner one. And you can see him with Carl McElwain, who actually was the thesis advisor of a number of the science team members. Craig Kletzing, one from the University of Iowa, who is the PI of our emphasis instrument. That's the magnetic fields and waves instrument. That was his thesis advisor. Barry Mock, my boss, is also I mustn't forget, so that was his thesis advisor. There, of course, is James Van Allen, George Ludwig, and Carl Pickering on the end, all feverishly finding the radiation belts. And on the next slide, you'll see a picture. I think they were quite happy there. But so that's the press conference where James Van Allen said we have radiation belts. The reason they are called radiation belts is he was actually out lecturing, and he was trying to explain where they were. And he was having some trouble, and one of the students said, oh, you mean like a belt? goes around like a belt. And he said, yep, that's it. So that's why they are the Van Allen radiation belts. Next slide, please. So here he is gracing the cover of Time magazine. In fact, not once but twice he got on the cover of Time magazine. And this was the original picture that we thought we would see in the radiation belts, this very stable inner belt, which we know is stable, or, well, we're going to find out actually how stable it is. But then the outer radiation belt, we also thought that was very stable when we first went up. So subsequent missions have then found that the outer radiation belt is extremely dynamic. But the puzzling thing to us is that it doesn't always react the same way. So you can have a nice solar storm coming towards you, and it causes the radiation belts to pump up, get really big, both in size and in strength. Another one can come by just a few months later and actually cause the radiation belt to shrink. And then, you know, a couple of months later, one comes by and the radiation belts appear to not even notice anything had gone by. Whereas the solar signatures all look the same or similar. Nice aurora with them all, but the radiation belt responses are very different. So what we know is that while we've made great strides on saying, hey, they respond to the sun, we don't really understand why they respond in different ways. So it's almost like making a cake, and you have your recipe, but you're not quite sure of the right quantities of what. And one day you get a flourless chocolate cake, and another day you get an angel food cake. And anyone who bakes understands that analogy. Next slide, please. Okay, so we have the two spacecraft. As Dave said, two are much better than one. No, we do not have one as a spare. There is a scientific reason that we have the two. If you are, I guess I'll do the ants on the cork because Mike likes the ants on the cork. So if you have two ants, or you have an ant sitting on a cork in a large bathtub of water, and it suddenly goes down and up, and it has no idea why it's really gone down or up, it just knows it went down or up. But if it has a friend, another ant, and in this we're assuming that ants can talk, clearly, and it says to the ant on the other side, did you just go up and down? And the other ant says, yes, I did. Or did you go up and down at the same time as me, in which case it was a really big feature? Or did you go up and down a little bit after me, a little bit before? Was it a bigger? Was it a smaller? And suddenly you start building up the picture of the dynamics. You also are going to have two spacecraft flying through the same phenomena fairly quickly. So instead of one spacecraft that would have to go around and wait 9 hours to come back, and goodness only knows what happens in 9 hours in the magnetosphere, you've got another one coming through very quickly. So that's why we want to have two. We continually vary the space between them. The orbits of the two spacecraft are very slightly different. So tomorrow morning at 78 minutes after launch, we will hopefully separate spacecraft A from the rocket. Then the Centaur will reorient, turn around, go up a little bit in apogee, re-spin up. These things are amazing, by the way. These Centaurs just really kick butt. But then it's going to spin up, and then it's going to spit out the second one. So they will be in very slightly different orbits. So the good thing about that is the orbit periods are a little bit different, and they actually lap one another. So so we're going to get continually varying spaces between the spacecraft as the mission goes on. What else can I tell you about this? So you see the orbit here cuts through the inner belt and then swings out. So it goes pretty fast down through perigee, and then does a nice cut through the inner belt, and then swings out, and we'll do a nice sort of longitudinal sweep through the outer belt, and characterize. So we're getting the inner and the outer, and thanks to an instrument that was contributed to us from the National Reconnaissance Office, we actually have a really nice high energy proton detector that will go up to 2 GeV. Which is really going to do a nice job of seeing what's in the inner belt. And then when we come through the outer belt, we'll go through the quieter regions where the HOPE instrument will be really important, where we're looking at that low energy plasma. And then coming out, the mag ice will pick up kind of in the middle range of the particles, and REPT will pick up the high end of the outer belt particles. So I know you'll probably know more about the instruments than I do, but so we have this nice particle suite that covers from the very, very low energies right up to the very high energies in the inner belt. We also have very nice fields and waves instruments. So when you look at the spacecraft, you see we have these long booms that come out from the solar panels. We put the magnetometers on there. There is a search coil magnetometer on one side that's looking at the sort of high frequency magnetic fields in the AC ranges. The flux gate, which is on the other side, that is looking at the DC, or the lower frequency magnetic fields. They're out on booms because we really want them to sample the medium they're traveling through and not tell me what's going on the spacecraft. So we have an unbelievably magnetically quiet spacecraft that Cooch will probably talk a little bit about. Just nod. Yes, absolutely. Okay, so he is now anyway. So it's a very, very, very quiet spacecraft, but we put them out on these booms so that they are really telling us what's happening in the medium. So there are also 6 electric field booms. So the spacecraft is spinning. One of the reasons it's spinning is we can put much simpler particle detectors on there and allow the spacecraft to take the particle through the entire magnetic field and pick up every single one of those particle populations or those different pitch angles or coning angles that they move around with. So that's one reason for spinning. The other is we have electric field booms. The ones on the top and bottom of the spacecraft are 6 meters long. They're stator booms. They're rigid. The ones that come out from the side, which you can't see on this picture, are 50 meters long each. So we're 100 meters across, or the size of a football field when those antennae go out. And they are thin wires. So spinning it, the centrifugal force keeps those out. So that's why we're spinning. What else can I tell you? So we've done why. Why do you have to get up so ungodly early? Is that... Okay, so apart from the fact that we've got less chance of an afternoon storm at 4 in the morning, which is really good, the other reason is this point of the orbit, which we call apogee, the furthest point away from the Earth, that actually walks around all of the local times as the mission continues. It takes us 2 years to go all the way around, plus a little bit. And the most interesting region scientifically is between local dawn. So if you look, when you look straight up and it's 6 a.m. in the morning, then that's local dawn, and that's when that apogee is there. Sweep that round to midnight. That's the most interesting region. If we go for 2 years, we can get that twice, as long as we start our operations at 6 local time. So it takes 60 days to commission. You have to bring those instruments on very slowly. So I'm afraid you'll have to get up to watch it at 4:07. But nighttime launches are way more spectacular, so I think you'll be really happy about that. So we've done why so ungodly early, and why all those booms sticking out. Okay, next slide. So this is a movie. The 2 dots represent RBSP. This is done using Sampex data. And you see the 2 of them, you actually see they're sort of chasing one another, and it does vary. Here comes a storm. So the storm, this is the DST, or the Disturbed Storm Time Index, in the top corner here. You're about to see it start with a storm, and those radiation belts are responding very dramatically. Not as dramatically as they will to a smaller storm coming up, actually. But so the 2 spacecraft, as we said, are lapping one another, and while they're also sweeping out, it's almost like petals of a flower. They're going to keep sweeping that out until we have the whole thing covered. It's a bit like a spirograph that you play with as a kid. I think we'll go on to the next one because this is a long one. Okay, so I did mention that we are doing fundamental particle acceleration. If you take an aerial shot of CERN and look down at that particle detector, you inject particles into it, they get energized. It's just a big radiation belt. That's exactly what we're doing. The particles are in our own magnetosphere. Common misconception, people think particles come from the sun and enter it, and that's what pumps up the radiation belts. It's the energy from the sun. We are very, very full of particles in the magnetosphere. It is not empty. There are a lot there. The particles are injected from within the magnetosphere and get very highly energized. So same processes are causing particle acceleration on the sun, giving rise to a lot of the solar activity that's then driving the radiation belt response. There's the large radiation belts at Jupiter, which is the most intense radiation. I think it's bad where we're going, but wow, that one would be really bad. And there's a nice picture of the Crab Nebula at the top there. Next slide. So nice artist rendition of the 2 spacecraft. Is this a movie or is this just a still? It's just a still. Okay. So we've done the instruments. We've done the orbit. Any questions? Yes. Oh, okay.
Are you largely going to be in an equatorial orbit, or do you have a high inclination so you can look at all parts of the belt, even the ones near the poles?
Nope. Awesome question. We are down at 10 degrees inclination. We want to get as close to the equator as possible. If you think about particle motion, there are 3 different ways that a particle moves around the field line. It goes round and round it. It also bounces almost from pole to pole, and it also drifts from magnetic field line to magnetic field line. So it's a kind of a complex dance it does around the magnetosphere. There are some particles that are almost field aligned, and they are the ones that are often lost, as Dave said, in the slot region or causing the aurora. There are some that that actually are kind of lying down at what we call a 90-degree pitch angle. So they're literally just staying in that equatorial region. So if we don't get right down to those particles, they are not going to get to us. So we have to lie down in that orbit. Yes.
Goodness forbid if there's an issue during the mission.
Of course
but
not.
if something were to happen to one of the spacecraft, how much does that change what you're looking at and the kind of effects you expect to see?
Well, we would still get great science results because the instruments that are flown on the spacecraft are literally the cutting edge, most sophisticated instruments ever flown in this region. And, even if you talk to some of my PIs, they'll tell you, well, we were selected in 2006, but new technology came along while we were, building, and we've even incorporated that into, so, we really are flying cutting edge instruments. So we would still get great science only, if we only had one. What we would lose would be this ability to really characterize the dynamics, particularly small-scale features. We really want to know, is this something that's changing in time, or is this something that's changing in space? And the only way you can really unravel temporal versus spatial is with two spacecraft. So that would be a big drawback, to put it mildly. It would certainly put a cramp in Dave's plans to get a Nobel Prize anyway, but assuming that, then we would still get great science with one. Yeah. Okay, and then my last slide, because I did forget one, didn't I, Mike? Thank you for bringing it up. Okay, so I was going to talk about radiation damage to satellites. So I always like to say our mission is a fundamental physics mission. We are studying particle acceleration. It's not just rocket science, it's just particle acceleration. And it's a fundamental process that's taking place all over the universe. But the really cool thing about this is it has practical applications, and here's just one. I know Dave talked in length about a number of different space weather effects, but really in the radiation belts, these are the things that we worry about for our satellites, particularly the outer radiation belt, because the inner one occasionally dips down and covers the space station, but this is really what we're worried about for our spacecraft, because your GPS are out in here, and goodness knows no one uses a map anymore. You just pull out a phone. I mean, seriously, you turn up at the airport and then you look up the address for your hotel in your email, and then you hit the button and it just tells you where to go. So I'm kind of really keen on my GPS, actually, so I really want to protect those. But all of your satellite communications, satellite TV, we don't even realize half the time what we rely on this space region for. So, we can have single event upsets that can cause computer errors, failures. You can have surface charging just because suddenly the medium you're going through is much more dense, much more particles, and it's just like a friction that you can get there. The particularly the things we all really dread, deep dielectric discharge, because that's often a killer. So that's actually why you put lots and lots of shielding around all of your electronics. And we are a sort of armor-plated spacecraft. We have aluminum shielding. It's about the thickness of a slice of bread. All around practically anything we can shield, we have shielded. I think it's basically the apertures of the instruments are about the only thing that are not covered in like armor plating. And then solar panel degradation, just hitting high-energy particles, just hitting your solar panels and damaging them. So we are doing fundamental physics. It has practical applications, and that really is my last slide this time.
My question actually comes from one of my Twitter followers. Garrett is here. He wanted to know if the probes are going to be named after the launch. I know right now they're just A and B, and when we were at the Grail tweet up together, so I know afterwards they were named after the launch. Will that be the case with these?
There are plans to rename the mission after the launch. I believe the spacecraft will always be affectionately known as the Radiation Belt Storm Probes, but there are plans to rename the mission. It hasn't been completely finalized what it will be, but I have always called them Van and Alan. They're my two babies. One is Van, the other is Alan. And I've worked with them for 11 years, and they're older than my children, so they are my babies. So.
Is there any gamma ray burst science on the either of the probes?
Not planned. I mean, we're certainly looking at that. You get these scientists. We're an awful bunch. So we build our instruments and then we work out what we can really do with them. You have your requirements and you build to that. But for example, Bern Blake is a cosmic ray fiend, and I absolutely guarantee that the first thing that he looks for is cosmic rays. So I'm not saying no, it's not a planned result, but as Dave said, the most exciting science is the stuff you didn't plan for. So nothing planned. Yes.
The picture you showed earlier with the three gentlemen holding the rocket, and
yes.
That's Drs. Pickering,
Von
Van
Braun.
Allen, and Dr. Von Braun,
yep.
The great rocket scientist. Obviously, that what we discovered about the Van Allen radiation belts really helped in the rocket design through all the ever since then.
Absolutely.
Do you think we're going to get more information now?
Absolutely.
That's really going to boost our
yes.
rocket designs in the future?
This is going to make dramatic changes to satellite design. And the models that we use to sort of estimate the shielding and the lifetime of spacecraft are more than 20 years old. And we know just with new data that some of them are over-predicting the medium and some are under-predicting. And that's both that is bad on both counts, because if you underpredict, well, I mean, obviously it doesn't take a rocket scientist to tell you what's going to happen if you underpredicted what the medium was like. But if you overpredict it, you've put too much shielding on. So you've spent more on launching it than you needed to. And anyone who works in the space industry will tell you lighter is better when you don't want to launch a tank if a Mini Cooper would have done. So you really do want to do much, much better at predicting what's going to happen. Also, operational spacecraft, if you don't want to underestimate the life of those and not launch one quick enough, nor do you want to overestimate, launch one and then leave it in storage, and now you've got two being damaged. You really do need to do a much better job. So this mission is tailored to really update those models. So the ones we use now are AE8 and AP8, and AE9 and AP9, there's already beta versions of those just waiting. It's like they've got everything else set up and they're waiting for RBSP, because this two-probe information is just going to really blow everyone out the water.
Do the two spacecraft talk to one another or just to the ground?
No, they're very antisocial. They just talk to the ground. That was a decision early on to save money, and they don't really need to talk to one another. The instruments do talk to one another on each spacecraft, however. So, if one particle instrument in particular suddenly sees a large increase in particle fluxes, it sends out a signal saying, hey, large increase. And then the magnetic field and the electric field instruments will go into a very high time resolution mode, and HOPE will respond by, instead of taking one proton and one electron, it will go into a fast electron cycle or something, so that we're getting a lot higher time resolution data.
Perfect. Thank you very much, Nikki. Next up, we have the chief engineer from the Applied Physics Laboratories Space Department. His name, as he told me to introduce him, is Cooch.
Thanks, Jason. I'd like to speak to you afterwards about scheduling me to speak after Nikki. She's a tough act to follow. I think you've all probably got the notion that the scientists are pretty enthusiastic about this mission. And believe it or not, engineers get enthusiastic about their work also. All of this is about all the science that comes back, and the engineers are very proud to be able to enable that science and the knowledge that brings back to us. So with that, I'd like to tell you a little bit about the role of the Applied Physics Lab in implementing this mission, and my role as chief engineer at the department. Before I get into that, I would like to thank Dr. Giles for the kind words that she said in her opening remarks about the performance of the Applied Physics Lab. Again, it is all about the science, but it is also very important to us as an institution to make our customer, NASA, happy with our performance. And to date, we've been very successful in getting to launch on time and on schedule. The really hard part starts now, and the payoff for all of that hard work. So with that. Next slide, please. The Applied Physics Lab is the implementing institution for NASA for the Radiation Belt Storm Probes mission. We designed, built, integrated, tested, and we will operate both spacecraft during the course of the mission. We also developed the ground system in concert with that. And we also developed one of the instruments that's flying on board the spacecraft, the RBSP investigation. Next, please. This was sort of a repeat performance in a way from the stereo mission that we also executed for NASA. Very similar in that stereo is an investigation that also uses two spacecraft. They're in a completely different orbit. They're in a heliocentric orbit around the sun, not remaining in low Earth orbit. But nevertheless, there were a lot of valuable lessons that we learned in the course of building two spacecraft concurrently, launching them and operating them, that we applied to the development of the RBSP mission, and I think helped make us successful programmatically in bringing the mission to this point, again, on cost and on schedule. Many of the same team members who worked on stereo also helped implement the RBSP mission, so that was another advantage to being able to retain that workforce and having good work for them to do. Next, please. Just briefly, in my role as chief engineer, I have to say I love my job too, and one of the great things about it is that primarily I give advice to people. I've been at the lab for 30 years. I've had my share of building a lot of hardware and delivering systems to launch. It's very gratifying work. It's also very hard work. And I'm more than happy at this point to sort of step aside and let other people do all that really hard work and to just give advice. The hard part of that, though, is that people generally only want good advice, which is a little bit harder than just giving advice. So I perform that function on RBSP. As you're probably aware, there are literally thousands of details that go into implementing a mission like this and executing it. And when problems arise, as they inevitably do during the course of the development, it sometimes is hard for the people who are in the midst of dealing with all those details to have an overall big picture view of what's going on. And so that's one of the functions that I serve is in that engineering oversight role, is to provide an independent assessment of the problems and the proposed resolution that the project would like to implement. I'm also responsible for defining and ensuring that the engineering teams execute these missions according to the proper processes and going through the proper reviews and doing all the things that we know are the right things to do in order to ensure successful missions after we launch. Next, please. Oh, I should say that another thing that I get to do is briefings like this the day before launch so that the members of the project team can actually remain focused on the job that they had ahead of them and make sure that they're well rested and ready for launch tomorrow morning at bright and early at 4:07. So what's easy about a two spacecraft mission? There are some things that are easy about it. There are some things that are not so easy about it. One thing is that both of the spacecraft are nearly identical. So we just kind of build two copies of most everything that we make. We take an approach with this mission, we have taken an approach with this mission as we did on stereo, to keep the design fairly simple. And I should have put the word relatively simple in there because I learned in the course of my career that there really is nothing simple or easy about any of this work. The complexity, even when you take a simple approach, to me still boggles my mind, and I regard it very often as nothing less than a minor miracle that we're able to do these things and get the science that we get back from them. Keeping them simple also makes them easy to test and operate, which is an advantage. It gives you some flexibility during the integration and test process. Sometimes if a problem crops up on one spacecraft, where you can sort of put that one aside, get a team to focus on solving that problem while the integration and test team proceeds with the processing of the second spacecraft. And some of the tests you run concurrently on both spacecraft. There's a discipline that we all follow in this community that we call test as you fly, which is part of the methodology, again, to ensure a successful mission. So we do things like when we vibrate the spacecraft, we vibrate them the way that they will be stacked in the launch vehicle, one on top of the other. We also run our acoustic tests like that, one spacecraft at a time. Other tests like thermal vacuum, we have to separate the spacecraft and test those separately because they don't fly together. At least they better not fly together after they've been released from the launch vehicle. So those are some of the advantages to doing a 2-spacecraft mission. Next slide, please. Some of the things that are not quite so easy about a 2-spacecraft mission, well, I said earlier that one of the easy things is that both spacecraft are nearly identical. One of the not so easy things is that they are not exactly identical. Now, this is not necessarily a hard thing to do, but there are some differences between the 2 spacecraft, and you just have to keep track of them as you go through the development. For instance, the 2 spacecraft mate to each other, so the mating hardware on one spacecraft is a little bit different than the mating hardware on another. The spacecraft talk on different frequencies, so you have to make sure that the right radios go on the right spacecraft, and you don't mix those up. And some of the signals from the launch vehicle while you're doing ground processing, it's called the umbilical harness from the launch vehicle, those signals are carried up from one spacecraft to another, so there's a little bit of difference in the harness. Again, not a hard problem, just something that you have to pay attention to while you're doing the integration and test process. Operating 2 spacecraft requires generally a larger operations team in the Mission Operations Center. A lot of the procedures that you use are identical between the 2 of them, but you still have to have enough people to be able to handle the operations for both, and particularly if, again, God forbid, there's an anomaly on one spacecraft that needs resolution, that you've got the manpower that you need to address that one while you continue to operate the other spacecraft. Also, if you run into a problem late in the game that happens to be a design problem that you, for whatever reason, didn't uncover earlier on the one spacecraft, well, that can mean that both spacecraft are affected, and you've got to take units off, perhaps, and effect modifications to both of them, and then get them both on the spacecraft. And I've already talked about the testing and the tests that you can't run simultaneously, that you have to break apart and then have two thermal vacuum chambers, say, to run those tests. So there are some pluses and minuses in doing this. Next slide, please. This depicts the RBSP spacecraft in its flight configuration. Both spacecraft combined are just short of 2,900 pounds in weight. The average power generation on each spacecraft is about 350 watts. They are spin stabilized. All the time they're in orbit, they're spinning at a rate of about 5 RPM. And they basically point the spin axis of the spacecraft towards the sun, which keeps the sun on the solar panels and keeps us in adequate power generation. The requirement for the mission life was 2 years, but we expect to be able to get 4 years of operation out of the spacecraft at a minimum. Most of the instruments are pointed out in this diagram. I apologize for all the acronyms. If we spelled out the name of each one of these investigations, it wouldn't fit on the slide. But essentially, there are experiments that are wave experiment-oriented, electromagnetic wave, electric fields, and magnetic fields. And that's what all the booms and antennas and sensors like that are for. On the bottom of the spacecraft are most of the particle detecting instruments. And you can see those colored cones at the bottom of the spacecraft. Those really aren't physical parts of the instruments themselves, but rather that depicts the field of view of each one of the instruments. And so that's always a very useful thing for us to put that visualization in there, because we have to ensure that there aren't any obstructions or interferences between the instruments on the spacecraft and the fields of view. Next, please. Okay, I've just got a few pictures of the development of the spacecraft. The environmental testing, again, this is the test as you fly approach that we take to qualifying spacecraft. We did something a little bit different for us with the RBSP spacecraft in testing the spacecraft to the acoustics environment that's generated by the launch vehicle, and that we don't have an acoustics facility, a dedicated acoustics facility at the laboratory, and we didn't want to take the expense to go and use Goddard's facility, which we've done in the past, because we didn't need any other of Goddard's facilities to test the spacecraft. So instead, we brought in a company whose main business is doing the sound engineering for rock concerts and things like that. And you can see the stack of speakers that they set up with the spacecraft in the middle. They were actually very excited to have this type of work too. It's a little bit different for them. And they enjoyed coming in and setting this up for us so that we could run our acoustics tests right there at the laboratory. The middle picture shows you the spacecraft stack on the vibration table, testing it for the launch vibration environment. And that smaller picture on the right depicts both spacecraft getting ready to be sealed up into the thermal vacuum chambers at the lab to do the thermal vacuum testing. Colloquially, we call this shake and bake, the vibration followed by the thermal vacuum testing. And next slide, please. Some more testing of the spacecraft. The spin balance test for the spacecraft. We actually balance the spacecraft the same way the tires on your car are balanced. And even though the spacecraft only spin at 5 RPM in flight, we spin them up at about 85 RPM in order to determine where we need to place balance masses in order to perfectly balance the spacecraft for flight. And that other picture there gives you, it's sort of a hard view to see, but it's the solar array deployment testing, which we have to take special measures in order to test adequately on the ground, because on the ground, of course, we have to deal with gravity that we don't deal with in space. But we do this, as a matter of course, to ensure that all the mechanisms and deployables on the spacecraft work. Next, please. As I said, we operate the spacecraft from our campus in Laurel, Maryland. We have a mission operations center that's configured to handle the operations of 2 spacecraft at once. It's kind of hard to see in that picture. You can see some large flat panel screens on one side of the room. And if you look very closely, you can see the same display, the same flat panel displays on the other side of the room. The room is configured for 2 teams of operators, 2 teams of engineers to support all the operations, being able to view all the telemetry from their subsystems. Next, please. And this is the 18-meter or 60-foot dish antenna on our facility at APL, which is the prime ground station for communications with the spacecraft. We also make use of some commercial backup stations around the world in the event that we need to bring any other assets online. But this is the main ground station for the mission. Next picture. This is a picture from this morning. It's really gratifying and exciting after having worked on something like this for 5 years to see it sitting on top of a rocket, getting ready for launch. It's a beautiful picture. We never get tired of looking at it. And finally, just a few more pictures of the spacecraft at various stages of processing down here at the Cape, being encapsulated in the fairing, and we're looking forward to a successful launch tomorrow morning. If there are any questions, I'll be happy to take them now.
Questions? Oh, don't be shy. There we go.
So when you do the spin test, do you have to put lead weights in to balance the satellites?
They're not necessarily lead, but that is the idea. Just as I said, just like the tires on your car are balanced, and we do a lot of analysis beforehand to understand how unbalanced we think the spacecraft will be before we have to put the balance mass on there, and we calculate how much mass we think we'll need and make provisions for where that mass will be attached to the spacecraft in order to achieve the proper balance.
Questions?
Are there any new significant design changes as far as the structure of the spacecraft or any other improvements as opposed to some of the previous missions like stereo that you're implementing?
Well, the answer is yes, and those modifications and changes were largely driven by the environment into which we were flying. So as Nikki said, the electronics boxes have walls that are about 3/8 of an inch thick, or about the thickness of a slice of bread, in order to reduce the radiation environment at the electronic piece part level. We also went to great lengths to shield the harness so that it wouldn't be damaged by the deposition of charges into the insulators of the harness, the insulation of the wire. That can cause charge to build up and can cause discharges that are both damaging to the spacecraft, but they also create noise and interference that interferes with the measurements that we're trying to make. The solar panels themselves had some special techniques applied to minimize any buildup of charge and resulting discharge in the panels themselves through the use of conductive grouting material in the buildup of the solar panels. So yeah, there were a number of things that we had to do that were basically driven by the environment into which we'll fly.
For this mission, was it feasible, or could have been feasible to put a camera on there to watch what's going on in the radiation belts?
It would have been feasible, perhaps, but I don't know that that would be very interesting to the scientists, particularly because of where we're flying and the type of science we're doing. You have seen images of aurora that are taken by certain spacecraft. Aurora are features that occur mostly over the poles, and we're not a polar orbiting spacecraft for one thing, so there really wasn't any value added in trying to put any type of imager, whether it was visible or UV or whatever. Did I get that right, Nikki?
Yeah, most things switch off their cameras. You've got so many particles and just sorry. So most cameras would actually switch off when they go through the belt. So you've got so much radiation. So if you remember when you see a big flare that hits SDO or SOHO and you just see that camera go, if you actually look at some of the auroral cameras, less than an hour after that, they are completely snowed out also. So you know that you're traveling and living in that. The one thing that would have been a nice addition would have been an ENA imager. So if you're familiar with the IMAGE spacecraft that flew and it did this energetic neutral atom imaging. It's a completely different kind of imager, and that would have been really looking at the ring current. That might have been a nice addition. It wouldn't be great on the platform, the particular orbit we have. You'd be better at a geosynchronous or something where you really, you know, or a polar orbit that IMAGE had to do a better job at that. But that would have been a nice addition. But we do have balloons, so we have a really nice. Barrel is the name of it. It's a collaborating balloon mission, and I think it's about 20 balloons that are launched from Antarctic, and they go up and they've got that nice, yes, thank you, yes, January of 13, which is why we're so dying to get up there, and they have a nice sort of fairly stable wind pattern, so they will go up and they're basically looking at the other end of the radiation belt. So we're looking at everything and why it's really enhancing and how the particle populations are changing, and Barrel is sitting there looking at the particles precipitating down, so they're really looking at the losses for us. So it's a really nice collaborative mission. So.
Any else?
How or would the design of the spacecraft have changed if the rotation of it were to have been, say, 15 RPM or 20 during a normal operational state, or even non-rotational?
A faster spin rate would have had implications for the instruments and how they collect their data. It also makes a difference in the amount of fuel that we would need on board in order to maintain a spin rate of that size, and then how much fuel it would take when we have to maneuver the spacecraft to keep the spin axis pointed more or less at the sun. As far as the engineering subsystems, not a lot of impact there necessarily, but this the spin-stabilized mode, of course, is a much easier mode from a stability point of view and the guidance and control aspects of it. And whether you're spinning at 5 RPM or 10 or 15 RPM there's not a lot of difference there. The main impact would have been on the instrument designs.
So
Yes.
you're the chief engineer, which means you get pulled in on all the really tough problems during the spacecraft development. What has you the most worried?
I have to pause because that's my boss who asked the question there. I'll be quite honest with you. I am not a huge fan of single-string spacecraft, and these spacecraft are. As an engineer, I like to guarantee mission success by having something to fall back on the spacecraft. Now, it is a fact of this business that we build a lot of single-string spacecraft, and over the years we have developed methodologies for how we test these things, how we design them, to ensure that they work even in the face, or even recognizing that we are always susceptible to stochastic failure, to random failures that somehow escape us from all the testing that we've done on the ground. That's the thing that I would probably worry about the most, but it's not something that I'm going to lose a lot of sleep over because of our history and experience in building spacecraft like this. Thank you, John.
Thank you very much for your time today. We appreciate you coming and talking to us. Next up here we have Ali Mendoza-Hill. She's with NASA's Launch Services Program, and she's the mission manager for this launch. So, thank you.
Hi, good afternoon. Speaking of acts to follow, you just get me. No pretty pictures, no presentations. Actually, just a correction, I am a mission manager in our launch services program, but I'm not the mission manager for RBSP. I wish. This is a really neat satellites, both of them. And the mission manager for RBSP is Rex Engelhardt, and you were supposed to meet him at the tour yesterday, but he got pulled away and wasn't able to meet you. But if not, he was a very interesting character. But I work for Launch Services Program, LSP for short. So when I say LSP, you'll know what I'm talking about. And LSP is the program here at Kennedy, and we are responsible for getting the launch vehicles for you, for the spacecrafts to make it on orbit. Here at LSP, we've got engineers, technicians, and a lot of support personnel, what we call the rocket scientists on the launch vehicle side, not on the brilliant scientist side. We are responsible for selecting a launch vehicle, and that process can start years before the launch is ready to go. What we do is we go out and procure, we take all the spacecraft requirements and we send it out to industry and said, we'll ask them who wants to bid on this launch vehicle, to launch the satellite. It'll come back and it's a rigorous process, and we'll analyze all the different proposals that come in and make sure what is the best and most effective ride for the satellite. At times it's very close, and it's just those little nuances that will have us select one vehicle over another. And in reality, the one that wins is the one that can best protect the spacecraft and get it into the right orbit and for mission success in the end, so we can get the science that would help and benefit us on Earth. Let's see, it's a beautiful rocket. This one, it's an Atlas V. It's a vehicle, if you've seen the configuration, it's a 401. All that means is a 4-meter fairing. It has no strap-ons around it. That's what the 0 is. And the 1 is that the Centaur, the upper stage, has only one engine. So that kind of tells you the nomenclature when you see that out there. We here at LSP, and depending on the satellite, we can select anything from small vehicles, such as a Pegasus that's air-launched from an L-1011, a Delta II from United Launch Alliance, or the big ones like Atlas V. So I believe Nikki was talking about the orbit that RBSP is going to be in. At apogee and perigee, you're talking about a difference of 300 miles on one end and 19,000 miles on the other. If you put that into reference, if you would drive from the North Pole to the South Pole, turn around and go halfway back, that's 19,000 miles, more or less. So you can kind of understand the orbit that the Atlas V is going to, and the Centaur will place the satellites in, the probes. Let's see, what else can I tell you about? We do launch out of, not just from here, Kennedy Space Center. We'll have launch vehicles that launch at different places around the Earth. We have launched from Kodiak. We'll launch from Vandenberg, which is out in California. We have Kwajalein, which is out in the Marshall Islands, and a couple other places. And pretty much the inclination will determine where we launch from. So like someone was asking about polar orbits, those we would launch out of the Vandenberg facility. So it all depends on the launch vehicle, where they can go, and where the spacecraft needs to go, where the launch site will be. Well, once we select the launch vehicle, and even before that, we do work closely with the spacecraft to understand what their requirements are. As he was mentioning, the shake and bake process, all that data is fed to the launch vehicles, so they ensure that the launch vehicle doesn't damage the spacecraft, and in turn, the spacecraft doesn't do anything to damage the launch vehicle or impact, its trajectory and its release of the spacecraft. So it's an iterative process, and it's very integrated. So LSP also manages that aspect in between the spacecraft and the launch vehicle providers, all the way from before selection. We'll go to different offers and get different analyses done through launch, and then once it's off the pad, it's all up to the mission ops. Let's see. guess for us here, that's pretty much LSP in a nutshell. I wouldn't want to bore you with all the details. As far as they asked me to tell you a little bit about myself and how I got here. Let's say I started here at Kennedy Space Center in 2000. So I am an engineer. Went to various schools in Florida, not FSU, so it's all the U, and FIU and Florida Tech. Sorry, 3, but not FSU. Anyway, so I have a bachelor's in industrial engineering, and I've got a master's in space systems, and I have a partial master's that hasn't been finished in mechanical. But I did start here at KSC in the industrial engineering group with shuttle, and so I worked shuttle until about a year ago, and I just transferred over to the launch services program. Kind of a different world, but not so much. We're still launching into space. We're just not launching humans. But the science is incredible on this side of the house as well. And one of the things, you go out and talk to the public, and they say, "Oh, what are you doing at Kennedy now that the shuttle's gone?" I said, we are making science. We are improving life here on Earth. There's so much more to do than just launching humans, and it's kind of, the science was kind of put under the belt of shuttle. So I think, we need to take the opportunity and get the word out that there is science going on here at Kennedy and all across NASA and all across the centers, APL, JPL, all the different science centers that help, the universities as well. That's pretty much all I have. I don't know if you had any questions.
Questions, anybody?
Yeah. My question I've been asking everybody here is, what do you want us as NASA social participants to communicate to the greater community in our society about how important NASA is and the science that's being done here that you've just elaborated on? And maybe you can also talk about your experiences as a woman in a man's world in this, and how people like yourself and the late Sally Ride, and how that's inspiring young girls in education.
Okay. I guess part of touching of what I was just mentioning on, a lot of people in the public will say NASA's all about just launching a shuttle and getting nice, pretty pictures when we come back. We're launching rockets like Hubble telescopes and just getting pretty pictures. In NASA and the science community, trying to launch these items and just get into space, we've developed a lot of science out there. We've helped just in like she was saying. Radiation technology. I mean, that helps. All that science gets fed back to the community. It's MRI imaging, it's cancer detection research that's going on. And a lot of the basis is used off of all the science that's developed at NASA, trying to go out to a radiation belt, trying to go to different areas. This science is all given out to the public again. And what we call is NASA spinoffs. So there's a website with NASA spinoffs that you can go out there and look at thousands of items. I don't know how many, but just everyday thing. Like we mentioned, GPS is it's the things we work on, laptops. All the technology behind that was developed as early as the Apollo program, and it just continues to develop. But no one ever sees that. So it's what's behind the scenes. It's not just that we launch a rocket and we just like to see the fireball at the end of the rocket and see it go high. There is a lot of science and technology development that happens in the process of getting to space. As far as a woman at NASA, I guess being an engineer, that whole I grew up with two older brothers, and they were always fixing their cars, and here was the annoying little sister asking, "What are you doing? Why are you doing that?" So as a little girl, I was always interested in how things worked, and we didn't have, how stuff works online, and we didn't have, dirty jobs on the internet and cable, so I found out by asking questions. And then moving on, so I was always that annoying little girl growing up through school, and I had professors and teachers that just, helped along the way. A lot of math, usually they said, girls, don't worry about math, go do something else. And I really enjoyed math. And I had some wonderful math teachers that just, helped me along the way. Women teachers as well as male teachers. And I think I played sports a lot as well. So I was a scholar athlete in high school. And I think being in that environment also just gave you a little bit more of I get exposure and just the how do I say it, assertiveness to just go out there and ask and do whatever you want to do, regardless of whether you're supposed to do something or not. If you like math, go for it. Doesn't matter if you're male or female. So in engineering, you are part of the minority as women in engineering, but we were all there to do the same thing. We all studied, we took the same tests. So you earn the respect of your peers by just doing the right thing. We're all accountable, you know, and that's how you just deal with it. I've never run across any issues, especially here at Kennedy Space Center at NASA. To me, there doesn't seem to be a, you know, oh, you're a woman, you can't do this or that. I don't know if I answered your question.
Because over the weekend, there was the issue with the Atlas V rocket, and you had an extra round of testing on Monday. How does this affect your launch team, and what role do you all have in that?
I wasn't actually involved in the discussions. Obviously, Rex is my cube mate. He's over on the side, my office mate. So I heard a lot of the discussions. But yes, they worked all through the weekend, and today is their rest day. So they're off resting, and so they're all just as excited to see, you know, to light this up and go launch. So it affects them when the issue's going on. It's the unknowns. There was a lot of on this issue with the rocket engine, you know, with the Russians and what we had, what we knew, what we didn't know about it. But once it was all resolved, I mean, that's kind of like, that was yesterday, and everybody's just moving forward. Once we know there is no issue and the risk is very minor, if any, everybody just puts it behind them, and it's the next day and the next issue. Ready for them.
Questions?
Is Launch Services program, are you going to be working with any of the commercial crew folk, either Sierra Nevada or Boeing?
We do have a few of our mission managers that are helping out. So as you know, as far as lessons learned through NASA, we do have lessons learned between programs. So we do have a mission manager on their team helping them out, as far as just even helping on the rocket side and just, you know, environments and all the analysis and just lessons learned over, you know. We've been doing this here at Kennedy since 1998. Probably LSP is involved in at least 70 launches through now with a probably high successful rate. So we know pretty much that integration side of things. So you've got the best of the shuttle guys that launched humans, and then you got best of the rocket guys that launched satellites, and you're melding together to make sure we're in the right spot.
I know you said that choosing which vehicle is best for the particular mission is what's involved as part of your job. How do you, and I know that you also mentioned that mission success is one of the biggest things that you put, that you factor into that choosing which vehicle, especially with a lot of the new vehicles that are up and coming. How do you classify mission success when choosing the next vehicle for a mission such as like RBSP?
One of the things we look at is, besides the current requirements of the spacecraft or the mission, we also look at past performance. So vehicles that have launched, you know, numerous missions we have a little bit more history on, but we also have groups in our office that are rocket specialists, and we're involved in oncoming vehicles. So in our arsenal of vehicles to choose from, we also have up and coming vehicles that we're looking at. They're not. They have to reach a certain certification point to bid for a rocket, but we're involved through their development. For instance, SpaceX. SpaceX, we have Falcon 1, and now just recently we have the Falcon 9 available to bid on contracts for us. We have the version 1. The Falcon 9 Heavy is soon to be, well, eventually will be on the contract as well, and we have in-house folks helping them develop. So our team is very integrated into the launch vehicles processes, as well as some of the spacecraft builders, and so you have insight, and we have a whole group of folks that are like the quality engineering folks. We also have independent engineering folks that aren't specifically LSP, but they do support us as well, which bring experience from different missions as well. So it's not just because you've launched before, you're gonna get the mission over someone that's never launched before. There is a give and take on how it's analyzed. I was saying it's a rigorous process, and we make sure that everybody has a fair shake at getting launching, and we want to promote the newer vehicles to come on board. So also Orbital we just on-ramped Orbital, their Antares vehicle, also onto the contract. So or the number of vehicles we can select from are growing, which is a great thing. So it gives us a little more options.
Last question.
In selecting which vehicles to use for various missions, how much does the environment of the launching site factor into which vehicle to use?
The environment of the launch site, that's more specific, like basically the inclination of where you're going. That's where they're determined. And different launch vehicle providers only have launch pads at certain locations. So for instance, a Delta II would have in the past been able to launch only from Kennedy. Now they're launching from Vandenberg. If you have a Falcon, you would be launching from Vandenberg. So that kind of limits also sometimes which vehicles can actually bid for different missions because they can't reach certain inclinations in certain orbits. Then you have the Pegasus that can launch off of a plane. So they pretty much have an open field, and so they have various sites. But it all really depends on that inclination. If you were asking as far as like weather, if like the environment at the launch site, you deal with it. You have storms on the East Coast and on the West Coast, depending what time of the year. You have winds, but yeah, we manage it, and we have the weather the weather folks on this side. We have the Eastern Range Air Force that manages all the environments for us and predicts, makes all the predictions and makes sure we don't launch in the middle of a lightning storm.
Thank you very much, Allie.
All right, thank
we
you.
appreciate it. Next up, we have astronaut Leland Melvin. He's currently the Associate Administrator for Education at NASA headquarters. So, welcome.
Good afternoon, everyone. How you doing? Come on, that was pretty weak. How you doing? I mean, you're here on the eve of a launch, not a shuttle launch, and here of a launch. I wish it were a shuttle launch. No, we want it, but that's not the case. Allie, that was great. Some great information, and thanks for that great information on RBSP. You're going to have a very interesting tweet-up opportunity today. We have some really cool people that you're going to have a chance to hear. And what we're trying to do with NASA Education is inspire the next generation of explorers. And you guys are our field generals to help get that message out, to get that message spread around the cosmos. And we've been doing something called the Summer of Innovation for the last 3 years, where we're trying to give hands-on experiential activities to kids in the summertime to help combat this summer slide that we've been having with kids in school. So if you can show the first slide, we've got a picture of a little boy at Dyer Observatory in Nashville, Tennessee, Vanderbilt University. We've done a lot of work with them with Summer of Innovation, and we have a very special guest from Nashville who's going to do some really cool stuff. Next slide. This is a picture of a little boy getting his pressure suit on. But these are the types of experiences that kids never forget. And we find that if you get a brain activated, if you get them thinking about themselves being the astronauts, being scientists, rocket scientists, all these people, then that gets them turned on, and they take those harder classes and they do the things required to become a STEMist. So next slide. Here's a little girl making her rover. She was making a rover for Curiosity Week. And then next slide. These are young boys that were looking up at the Venus transit. And when I think about explorers, we all look up into the sky. We look up into the heavens to see what's out there. And as we tweet and as we send our messages around the cosmos, it goes through the sky, comes down. But we have to use sometimes alternative ways to get kids inspired, whether it's sports, whether it's music, no matter what it is. And so the next person you're going to hear is a good friend, singer-songwriter, Beth Nielsen Chapman, who's going to entertain you a little bit with some of these songs that relate to the mighty sky. So come on down, Beth. Let's give her a round of applause.
You rock star.
Hey. We got rock stars in the house, y'all.
All right, it's great to be here. And I'm from Nashville, Tennessee, which is the vortex of songwriting, just like this is the vortex of space exploration. And myself and Rocky Alvey created this little project and actually tried these songs out on the children from Summer of Innovation. And we think of songs as a great can opener into getting all that information. And this song's called The Big Bang Boom.
Audience participation.
That's right. Y'all have to sing on the boom. It sounds like this. Boom, only really loud. Okay. Since all of you.
Boom!
Yeah, and he's going to be the conductor of that. Ready? Here we go. The universe is the strangest place. Started with the Big Bang, boom. Created time, also space. Way back in the Big Bang, boom. No galaxies or stars to see. Way back in the Big Bang, boom. An expanded singularity. Way back in the Big Bang, boom. The Big Bang boom, the Big Bang boom. Started with the Big Bang, boom. All the universe's room. Created from the Big Bang, boom. Excellent. I'd like y'all to all come out on the road with me. At first, no atoms could be found. Way back in the Big Bang, boom. They all were formed when it all cooled down. Way back in the Big Bang, boom. Oh, and galaxies die far. Way back in the Big Bang, boom. An expanding singularity. Way back in the Big Bang, boom. The Big Bang, boom. The Big Bang, boom. Started with the Big Bang. Oh, the universe's room. This one has to be really big. Created from the Big Bang. Oh, you guys are so good. Galaxies, they fly apart. Closer at the very start. You can see the flow so very small. You can see the first light shine. Telescopes look back in time, and in your hand you could have held them all. The Big Bang, boom. The Big Bang, boom. Started with the Big Bang, boom. All the universe is room. Created from the Big Bang. All came from the Big Bang. Boom! Started with the Big Bang. No! Do this part with me. One more. 1, 2, 3. Boom!
Do we have any questions? We're going to do a couple more songs, but do we have any questions from the audience so far? Yes, sir.
When is Will.i.am going to drop the Mars song?
When is Will.i.am going to drop something? Is that what you said?
There's the song he was going to do for Mars.
Patience, my friend.
Okay.
Patience. Any other questions? Anyone else?
Don't be shy. Questions?
As a fellow singer-songwriter myself, what got you inspired to do the science lyrics and the creativity in your music?
Well, that's a great question. Well, my co-writer, Rocky Alvey, who is the director of the Dyer Observatory in Vanderbilt in Nashville, had these lyrics and some of the songs started, and we'd been working together over the years, and I said, you really need to do an album, and so I got kind of pulled into it because the words were so interesting, and I'd never really known a lot of the stuff about astronomy, and that's the great thing about the way songs can kind of give you this entree into remembering all the information. So we've just had so much fun working on it. It's the most fun I've ever had making a record, and I've been making records for 30 years. So it's been really a blast, and especially fun to watch kids get excited and see the light bulbs go off in their heads.
Here's Rocky back here from the Observatory.
Yeah, hey everybody. I'd say one thing that's I can say about this album and the songs is NASA has been a huge part of an inspiration in my life from the time I was a kid. One of the first memories I have of the sky is watching a satellite go across the sky when I was about 8 years old. As a result of those experiences, you know, I wrote these lyrics and songs, and Beth and I put it together. Our whole deal is turning kids onto science. And Summer of Innovation has been such a wonderful thing for us at Dyer Observatory because we've been able to, through Summer of Innovation, interface astronauts and physicists, scientists of all sorts with these kids who never have that experience. And so our whole thing is getting kids, they may not end up being scientists, they'll be more scientifically literate, but and some of them will be scientists. We've had several multiple years of EPO grants from NASA, and that has allowed us to connect kids who'd never get connected with these great astronauts and scientists. So like Leland,
that's right,
who's there this summer inspiring kids. So.
And I think one of the other things that, you know, I think about Stone Soup making this education piece a partnership. You know, NASA has a piece, singer-songwriters have a piece, you know, astrophysicists have a piece, private sector has a piece, and we all play in this together. I mean, you guys sending tweets out right now probably know of many school teachers that you could go and talk to about the programs we have at NASA that could help inspire some of those kids, or even the programs that we have for teachers to get them more prepared to be better science teachers. And so I think that's really the special sauce about all of this, is that one organization cannot do it alone. It takes parents. It takes parents to be involved with their kids' education also, which a lot of parents really don't understand the science. But, you know, we have programs that say you don't have to be a scientist to raise a scientist, and we teach parents the things that they need to do to get their kids to become scientists and engineers. So that's another piece of this pie. And we just had a really cool person walk in, our administrator, Charlie Bolden. Come on up to the front, sir. Four-time flown shuttle astronaut, and he's also got a call sign by the name of Panther.
Yeah, not going there.
Not going there? How you doing?
I'm doing well. I'm doing well. I came by, as I usually like to do, to welcome you all and thank you for coming. You know, I was sitting in the back, and I've had the experience of watching Beth do her thing for a while. And I will add something to what Leland said that I think is really important. And shortly after I became the NASA administrator and we sat around, we had an educational, I guess we call it an education summit, where we brought representatives in from colleges and universities, museums, and the like, about 25, 30 people. And we were looking for help in trying to make our educational program more effective and enabling us to reach more kids about STEM education, because the president, when I talked to him about taking this job, the first thing he talked to me about was inspiring kids to want to get into STEM education and STEM fields. And so that was the deal we made. If after the first year I didn't have Leah and Sasha, Sasha and Malia interested in math and science, then he could fire me. I think they're interested in math and science, at least I hope so, with a mom and dad who really push it the way they do. But on that day of the summit, you know, what we wanted to name the summer was Summer of Science. And it was interesting because there was a representative from, I think it was the Boston Museum of Natural History or the Boston Art Museum, and he raised his hand and he said, let me make one recommendation. He said, whatever you do, don't put science in the name. And we went, wow, help me understand this. He said, what you're going to do is you're going to turn kids off who don't know that they're interested in science and engineering. He said, because they're afraid of it. He said, what you're trying to do is overcome their fear of science because they have teachers who are afraid to teach it. And it really stuck with us. And so we started thinking about things you could do, and that's where the innovation came from. You know, and it's just one young man who represents the Society of Black Engineers. He had heard me talk about inspiring kids all day long. He said, I have had it. He said, you know, you keep talking about inspiring kids. We are not going to be able to inspire anybody unless we can bring them out where they see what's available. So you've got to make things available to them first so that they know they have something about which to be inspired. That's what Beth does. You know, I sat in a pub, in many pubs, in Dublin, Ireland, with Beth, and watched her work her magic with people she had never seen before, but people who have a love of music. And then as she played through the night, to get engaged in conversations with people about space and about science and about those kinds of things, that conversation would have never happened had it not been for somebody bringing it to them to let them know that it was available. And so that's what Leland and his folk are trying to do. They're just trying to make sure that kids know what's available so that they can be inspired. So the Summer of Innovation is about trying to reach two groups of people. And in my mind, the most important group we're trying to reach is the teachers, because we can touch 1 million kids, and we've touched 1 million kids. If we touch 1,000 teachers, let me tell you, it is countless how many kids you reach. So by reaching you all, I mean, how many of you sitting in this room? We never did this stuff before, and you've heard me tell you this, how much I appreciate your being here. We will reach more people today by your being in this session than NASA has ever been able to reach in doing things the way we used to do them, where we depended on people trying to find a place in the country that had NASA TV, or trying to find any media outlet that would even mention NASA, you know, other than the first few years of the space shuttle program. People talk about NASA and us and you every single day because you're communicating with them and you're telling the story. And so I can't thank you enough for what you do, because you bring a different medium to our ability to reach people, not just kids, but people. But the kids are really important, and the teachers are important. So I'll thank you for that. I don't think they want me to stay very long, but we can keep trying to see if you have some more questions that I can answer for you. And if I can't answer them, I've got my driver in the back. I'm just kidding. No, Waleed, raise your hand. Waleed Abdelhadi, the guy in the white shirt back there, is the NASA chief scientist. He is fascinating. He is a former NASA employee who is a college professor. He's a professor at the University of Colorado, but he's been with us for almost 2 years now, working as the chief scientist. His passion is ice. He's a glaciologist. He's a glacier guy. And he's really upset right now because he's running out of glaciers, and all, as he's concerned, as are we all. The other fellow back there with the much more formally dressed, David Rasnowski with the glasses on, is the NASA chief of staff, and he loves getting out and having an opportunity to talk to people, something the chief of staff did not ordinarily do, but he's incredibly good at it, and so I try to get him out. And then the star of the whole team is the guy with the yellow tie on and the blue shirt, David Weaver, who heads the communications effort out of NASA headquarters, and he and I go back and forth a lot. And I have to remind him, he's passionate, I'm passionate, we both cry, and it's because we are so passionate about what we do that we don't always agree on things. But I can always count on David telling me how to get the message out. And if I'm smart enough, I do it. And on days that I think I'm smarter, I don't, and it turns out to be a really bad day. So I'm learning. Anyway, so there are other members of the team, but yeah, who else is back there? Oh, Deborah's back there, the chief. Deborah, step out for a minute, because we're getting ready to lose Deborah. Deborah is a White House fellow. And we've been privileged to have her on the team for almost a year now. She will leave next week and wants to go back and do some things in education. And so I promised her I was going to help her in every way I can because she really knows how to do things. And so she's been in the office with me for a year. We've been privileged to have 3 consecutive White House fellows. And to tell you, if you've never met one, they are really, 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 really sharp. So Deborah, I didn't get a chance to thank you before now, but thanks very much for the year with us, and talk to some of these people sometime. Anybody have a question that I can answer for you? Yes.
Hi, this is less a question than a thank you from my son, who's also named Charlie. He was able to go through the shuttle experience yesterday at the visitor center, and he really enjoyed it. So you're inspiring.
Thank you. Thank you very much. That was fun doing that. And I, for anybody who doesn't know who she's talking about, the shuttle launch experience over in the visitor center, it was really a lot of fun putting that together with Bob Rogers and a whole bunch of other folk who came in to help us with that. And it's great if you haven't had an opportunity to do it. It's the closest thing to going to space, to be quite honest, so without going there. Anybody else? Yes.
Yes, I have a question. I'm a recent participant in the NASA EPDN program, and that was affiliated with Georgia Tech.
Yeah.
And as a teacher, I found it interesting is even though this was a very much a free program for teachers, STEM teachers, I only found 50 or 60 teachers within each of my classes. I would expect something to be more like thousands of teachers throughout the world. What can we do within the NASA social community that we have here right now to help promote the STEM teaching cause that you guys are so well promoting?
Tweet nasa.gov/education and point to the EPDN work that we have there. I mean, you went through it. You did the robotics?
I actually did the continuing network with all the online teaching tools.
Okay, but again, it's a messaging thing. If we can get it out, multiply this room by thousands that have access to NASA education, Twitter, and social media, avenues, and it's just a continuous process. And Charlie said it. We have to use you guys as better tools to get that message out. So it's a lot of things like that. We have a lot of content out there that teachers don't know about that they could be using. We have instruction materials, rocket guides, so many different things. But it's a messaging piece. Yeah.
I just wanted to thank you for the free Xbox MSL game. My 14-year-old actually got engaged. If in version 2 you can add the Master Chief, you will hook him.
Okay.
Very cool. I'm a recent graduate at the University of Florida, and I was part of an AIAA group there that would always put on like a yearly outreach to middle school students, try and get them involved in space. We call it Aerospace Day. Yeah. And I know that NASA offers a lot of opportunities to have speakers come. I know if you have a big event, you can have an astronaut come. What are some ways that we can help get NASA involved in an event like that to maybe bring even more than just one middle school, maybe involve like the whole town or something like that in an event like that?
One of the things. Yeah. Go ahead.
Go ahead. I was going to say, the more the merrier for us, to be quite honest. For you, it would be KSC probably, unless you're going to go to another part of the country. But every NASA center has responsibility for a segment of the U.S. And every state has a space grant consortium, which operates usually out of the land grant university for that state. So I would say, if you're from somewhere that doesn't have a NASA center in it, you're from Minnesota or Montana or something like that, just go online and find out where the Space Grant Consortium is, and it's probably out of the land grant college in your state, and then see if they can help you put together a venue where you're going to have a lot of teachers or a lot of students or a lot of both, and then either go through Leland and Education or through our communications office. If you're down here a lot, you can go through the communications office here at KSC. But I would say that's one thing you can do.
Space Grant's probably the best way to go because they have a network of other organizations that are part of them. They could bring in even other people that are NASA-centric, NASA-based. So that's a good way to do it.
And the other thing I would tell you, I would not limit it to, just let your imagination run wild. We went to a oh shucks, David. We were at the National Museum. What's the museum in New York? American History Museum, and they had a night that was incredible, and it turned out to be a space NASA night and everything. Niels deGrasse Tyson was there for kind of a talk, and then we all went downstairs and stuff. But it wasn't your typical NASA crowd. It was young entrepreneurs who were interested in tech stuff, high tech. And by the end of the evening, they had a really good idea about NASA and the kind of stuff we did, and they were all looking for ways that they could get involved, whether it was their business or just because they had a particular interest. So the only thing I would tell you is, don't limit it. Again, going back to this, don't do the science thing. Don't limit it to a particular group of kids because you think the others are not interested. Get a bunch of athletes. Leland can tell you about this. He's been with Donovan McNabb and at the Donovan McNabb football camp teaching the physics of football to kids who they didn't know they were going to even hear NASA. They came out to the Donovan McNabb football camp, and Donovan talked about why he throws a tight spiral and why it gets to where he wants it to go. On TV, every once in a while, you'll see Kurt Warner. If you're a football fan, Kurt Warner, multiple-time MVP in the NFL with the St. Louis Rams. Kurt does a public service announcement now, a real quick spot, and he talks about the physics of football, and he talks about math, trigonometry, and geometry, and how he mentally calculates how he gets the ball, how he got the ball to the receiver, and why he was as good as he was. You know, everybody thought he's a bartender, and he said, you know, I know a little math, and just gauging the speed, the velocity of somebody going from that point to that point, and trying to figure out what angle you have to lead it by. That's math, and so I would say try to get kids, whether they're in music, athletics, anything, bring them out. Let them talk about sports, let them talk about music, but then throw a little stuff in, and if we can get an astronaut there or a space technologist, I can guarantee you they'll figure out a way to tie what we do into it. So I would definitely don't focus just on kids that people tell you, you know, are interested in science and math, and those are the kids that are really serious, because I don't think we know, to be quite honest.
Okay, we're going to have another song from Beth real quick. Yeah. David, do you have something?
Thank you. Awesome.
So, again, it's great. I can't believe I'm standing between these two amazing people in the world at this moment. But speaking of STEM, we've been designing STEM lesson plans for each song on this little collection of songs called The Mighty Sky. And this is the title song. It's called The Mighty Sky. Feathered clouds of golden hues are fashioned by the gentle winds. A silent dome of stars appears. The canopy of night descends. Hidden treasures then are found. Their subtle glories greet the eye. And the gifts of peace are handed down to watchers of the mighty sky. Flying through Orion, you would have to go so far, through Proclid fires to Cassiopeia star. Squint your eyes, outstretch your hand, and hold 1 billion galaxies. More stars than are grains of sand, and each with countless mysteries. Though our feet are bound by earth, in our hearts we all can fly. And imaginations are since birth as children of the mighty sky. So let us sail past Earth's blue veil along celestial streams. For all of this, our compass is our dreams. Ooh, hidden treasures then are found. Their subtle glories greet the eye, and gifts of peace are handed down to watchers of the mighty sky. Like Stephen, Leland, Melvin, the mighty sky, the mighty sky.
Great job, Beth. Any other questions?
Questions? Don't be shy now.
How did you get involved with NASA in your young childhood?
Young childhood. I had an experience with a non-age appropriate chemistry set that I mixed these two dissimilar chemicals together and created the most fantastic explosion ever known to humankind. And that flipped the bit in my head, and I became a chemistry major in college and played sports, played football, did a lot of different things. But it wasn't until I started working at NASA Langley that a friend of mine said, "Leland, you'd be a great astronaut." I'm like, "What are you talking about? Astronaut? I don't know anything about an astronaut thing." And he handed me an application. I looked at it, put it down, and then another friend of mine, Charlie Camarda, who was a good friend, we worked on a project together, he got into the Corps that year. And so I said to myself, well, if NASA's letting knuckleheads like that into the astronaut corps, I can get in. So I applied the next year and I got in. But it was one of the most fantastic things. And, you know, Charlie's flown 4 times, deployed the Hubble, I mean, done all this stuff. But those things pale in comparison to when you inspire a kid to do whatever they want to believe, whatever they believe in. And I think the part of education, coming from being an astronaut to being in charge of education now, is one of the most rewarding things that I've ever done, because I see kids that have never, in their wildest dreams, would have thought about being a good scientist or a good engineer. And I'll tell you one story. I was giving a presentation at NASA Goddard, brand new astronaut, first time, had never flown or anything. These kids walked in, they fell asleep. I was showing a picture of Dr. Bernard Harris, who was the first African-American astronaut to do a spacewalk, medical doctor too. This young girl woke up, looked up, saw him, heard me talk about him. She fell back asleep. And I said, I really must be a horrible public speaker. But 5 years later, I was at a conference, and this young girl walks up to me and she says, Mr. Melvin, I remember hearing you talk about Bernard Harris 5 years ago. And now I'm going to medical school, and then I'm going to be a doctor. So you never know who you're going to impact. You never know when they're listening. And it's just so important that you have a good message and something to share with them. So I think we all can do that with this technology that we have in our hands and in our pockets. Especially, you know, I think about Angry Birds. You know, 10 million copies of Angry Birds was sold in 3 days. That's a multi-millionaire. And if we can get these kids to start thinking about being developers of the technology instead of just users of the technology, let them program the iPhone and the droids and create something as a middle school student, they'll be the next Steve Jobs. So we have to get them thinking about the development piece versus just the user piece. I think that's what I did as a kid, blowing things up and getting in trouble for burning holes in my mother's carpet, you know. Thanks.
Questions? Other questions? Sure.
So you mentioned Angry Birds, and there's a space version of Angry Birds. Can we put a radiation belt level in that space version of Angry Birds?
David Weaver, Carl Rubio.
Opportunity to promote my mission. I'm sorry.
We can do anything. We're NASA.
We're NASA. Okay, so we'll talk.
Okay,
Great.
we'll talk. We'll talk. Okay. Any other questions?
Questions?
Any comments? Besides questions, any comments?
This isn't specifically about RBSP or education, but does NASA have plans for another leadership? I think they're called leadership class mission, like Curiosity, in the couple $1 billion range?
I'll let my boss handle that.
So at one point I read about there's different classes based on the kind of the price of the mission, and that Curiosity was the highest, the leadership class, flagship class. Does NASA have plans for another one of those in the next few years?
Let me talk very quickly about flagships and other kinds of things. We are always thinking about flagship missions and always working with the scientific communities. Waleed will tell you, we're lucky in that we get input from the scientific community every 10 years. And almost every time, and it's in specific classifications like earth science, planetary science, and the like. And they frequently like to present to us a proposal for a flagship mission. What we're trying to do right now, and one of the things we asked the folk in the Mars Program Planning Group, is to look at where NASA's budget sits today and look at where it looks like we're going in the future and come up with something that accomplishes the objectives of a flagship mission with a less than flagship price tag. You know, if you look at, well, we just announced a mission called InSight the other day, which is a Discover mission. And that's I think, I got to get this right, the lowest price mission we can. But it's the closest we're going to get to date to a sample return mission, because, you know, it's gonna study the, what do I call it, the crustal if we were here on Earth, I would call it crustal deformation. Earthquakes and stuff like that. We're looking for seismic activity on Mars. We're looking for ways to get samples of soil and other kinds of stuff. It's not going to scoop, but it's going to look deep into the Martian surface. We have to figure out a way, an affordable way, to get a sample back from Mars. So answering your question, we're always looking at flagship missions, but I look at them from the perspective of what are the scientific objectives that the community wants us to accomplish, and then I challenge the team to say, okay, this is what they want. We can't give them a $1 billion mission, but we can give them $1 billion worth of science, you know, for 450 million or whatever it is. And sometimes we can't. And when that happens, then we can go forward then to the Congress and the administration and say, this is a critical science objective if we're going to do this. If we're going to put humans on Mars, we have to do this. We have combed everything we can think of. We cannot come up with a way to do it other than this type of mission. So I think what you're going to see us do in the next few years is talk more and more about downsized missions, you know, that accomplish big objectives, but don't have the price tag on them for a little while anyway. I don't know whether that answers your question. Yeah. It's always people don't like to hear that, to be quite honest. And I'll share with you something. We actually have people in the community who I think have been disappointed that my enthusiasm over curiosity is while robust, I'm not saying that, okay, curiosity was so successful that we're going to go out and NASA's budget is going to be doubled. That's not going to happen. You know, that's not realistic. And hopefully you all understand that. You know, it's just, look at the fiscal time. Look at the situation the country is in right now. And it would be irresponsible for the NASA administrator to go in and say, look what we just did, we want to double our budget. I would love to do that. But the probability of that occurring is not very good. And so I want to go in with a credible proposal, and this is what I've said from the day I testified at my hearing to be confirmed as the NASA administrator. I want to bring you things that are realistic, that are affordable, and that are sustainable, that are going to last through multiple administrations. And so that's what we're trying to do. And if I went off and told people we're going to do flagship mission in every field right now, I'd get laughed off the planet, because that's not realistic, you know, and also not sustainable and not affordable. So it wouldn't meet any of my criteria. Question over there, comment.
So if somebody were to hand NASA a blank check and say, go do one of whatever you want to do right now, what would your wish list start with?
I don't have a wish list for that. I really try to focus. I depend a lot on. I'm not the smartest guy in the room. I don't go to any meetings where I'm the smartest guy in the room, and I know that. And I really depend on the leaders in the agency to advise me on where we ought to be going. I love education. My mom and dad were educators. I don't tangle with Leland when it comes to education, you know, because Leland has a professional team, people who spent their life in education, and they may not always have it right, but they got a lot better idea than I do. And so it would be foolhardy for me to try to tell you this is my dream. I don't have one single thing. I want to do everything. That's why I'm the NASA administrator. But I have incredibly professional people, competent and capable people, who say this is what we should try to do now, because that's the next logical step, you know, to putting humans farther in the universe than we've ever been before. My granddaughters tell me they think I'm short-sighted because I always talk about Mars. Well, for me, you know, that's the best conceivable destination for humans right now. I'm not 6 years old like my youngest granddaughter. My youngest granddaughter thinks about going, you know, beyond the solar system. When I was her age and I thought about going to Mars back then, you know, in the 50s, I was just like them thinking about, you know, going warp speed and all that kind of stuff today. To them, that's going to happen. To me, Mars was going to happen. And I still think Mars is going to happen. And I am dedicated to that. So, you know, we don't work fast enough for a lot of people. And I wish I could tell you some one thing that I would like to do. I don't ever get to talk about aeronautics very much in this group. You know, my passion, my heart, my gut is in aeronautics because we do incredible things for the nation with our aeronautics research. You know, you can fly from point A to point B faster than you've ever done before, safer than you've ever done before, in cleaner airplanes than ever before, quieter airplanes, and I will brag about it. That's because of NASA Aeronautics, and they do it on a shoestring. That's where I would like to get more money. If you want to, is there something that really is grossly underfunded? It's aeronautics, to be quite honest, and that's the big A in NASA. But just through the years, it kind of dwindled. But the people did not give up on their dedication to the field, and so that's why we still do great stuff. I have talked too long, and I've got to go. But again, I want to thank you all very much. You said one more question? Yeah, oh, one more question. I'm
Hi.
sorry.
I just wanted to take this opportunity to thank you for NASA's commitment to education. I went to college on a space grant scholarship, and I'm now part of the RBSP science team. And I'm really thrilled with the launch coming up, so thank you.
I'm not going to say another thing.
Well, I like to say that this has been a very moving experience for me because Beth Nielsen and Charlie here have, they always inspire me when they talk and when they play, and I'm just very, very humbled and blessed to have them here. Do we have time for any more questions or a few more questions, or we just want to wrap it up? One right here? Yeah.
Hi, I do a little bit of outreach with an observatory where I live, and my question is kind of along the lines of Neil deGrasse Tyson. You know, children are great, but they're kind of naturally curious. My thing is always with adults, the parents that are going to be influencing this child's life for the rest of their lives. How do you get the adults to kind of get out of their stuck in ways? Because they're quite honestly sometimes harder than children to influence in that manner. Children, can be kind of more easily influenced. What kind of programs do you do any work with adults, or do you have any insights on that?
We have a program called SEMA, and it's where we actually have kids come in on the weekend we have these SEMA sites where the kids do hands-on stuff. They build robots. They have little weather stations. They do programming and different things. But we also bring their parents in, and they're taking classes and understanding about the things that their kids need to be scientists and engineers, and they're understanding about what it's like to see their kids building a robot. And then we tell them, you can go home and do these other types of things. You can go to our website, nasa.gov/education, and do projects with your kids at home. And so that's a way to get them engaged. But also, we have other outreach programs. David Weaver's shop is trying to get more community-based type things where we have an astronomy night, and parents and Neil deGrasse Tyson's come, and the whole community comes out to see and witness this type of activity. And so the kids are inspired. The parents are now starting to understand what it means to grow a scientist or an engineer. And those are the types of things I think that will help the community and the parents get a better understanding of what they need to do for their kids. And it takes you guys to spread that message too. You have parents, you have grandparents. Share that message with them. Go talk to a teacher. Those are all ways to spread that message. All right.
Perfect. Thank you very much for joining us today.
All right. Thank you.
Well, everybody, that concludes our NASA Social for today for the launch of the Radiation Belt Storms probes, which is scheduled to happen tomorrow morning in the wee hours on Friday morning at 4:07 a.m. Eastern Time. We hope that you'll follow along online by following the @NASA or @RB Storm Probes Twitter accounts, or you can like us on Facebook on the NASA or the Radiation Belt Storm Probes pages, or you can follow NASA by putting us in your circle on Google+. Make sure to join the conversation or follow along using the #RBSP hashtag, and for the NASA Social event, the #NASA Social hashtag. Thank you all very much for joining us here today, and we hope that you've had a great experience and learned a little bit more about this incredibly interesting mission. Thanks, everybody.